Have you ever wondered what powers the magic behind those incredibly insightful AI responses you see online? What's the secret sauce that allows machines to understand and generate human-like text with such nuance and accuracy? I mean, really, what is it? Is it just a bunch of ones and zeros, or is there something more to it? Something coded? We've all seen the impressive capabilities of large language models, the way they can answer complex questions, write creative content, and even translate languages in real time. But behind all that seemingly effortless intelligence lies a vast and intricate system, a system built upon what we might call the Gemini text code. Now, that's not a formal term you'll find in any official documentation, but it's a useful way to think about the underlying principles that make Gemini and similar models function. We're going to dive into the core concepts that contribute to this code, breaking down the complexity into understandable pieces. To understand this Gemini text code, we need to start with the concept of a transformer network. These are the architectural backbone of modern large language models. Think of a transformer as a sophisticated system that processes sequences of data, like words in a sentence, by paying attention to the relationships between them. It's a bit like how we, as humans, understand language. We don't just process words in isolation, we consider the context, the surrounding words, and the overall meaning. A crucial component of the transformer is the attention mechanism. Imagine you're reading a sentence and trying to understand the meaning of a particular word. Your brain naturally focuses on the words that are most relevant to that word. The attention mechanism in a transformer works similarly. It allows the model to assign different weights to different parts of the input sequence, effectively focusing on the most important information. Mathematically, this involves calculating attention scores, which are used to determine the relative importance of each word in the sequence. You might see this expressed as a scaled dot product attention, represented as where Q, K, and V represent the query, key, and value matrices respectively, and dk is the dimension of the keys. This formula might look daunting, but the core idea is that it allows the model to learn which words are most relevant to each other. Now, transformers are trained on massive datasets of text and code. This training process is where the model learns the patterns and relationships that exist in language. It's a bit like teaching a child to read and write, but on a much larger scale. The model is presented with countless examples of text, and it learns to predict the next word in a sequence. This process is called self-supervised learning, and it's a key factor in the success of large language models. During training, the model adjusts its internal parameters, or weights, to minimize the difference between its predictions and the one actual text. This process is called backpropagation, and it's how the model learns to improve its performance. Essentially, the model is constantly refining its understanding of language, becoming better and better at predicting and generating text. 1. GitHub.com. GitHub.com. But it's not just about predicting the next word. Large language models also learn to understand the semantic meaning of words and phrases. They learn about the relationships between concepts, the nuances of language, and the subtle ways in which words can be used. This understanding is what allows them to generate coherent and meaningful text, even when faced with complex or ambiguous prompts. Another critical aspect of the Gemini text code is the use of embeddings. Word embeddings are numerical representations of words that capture their semantic meaning. They allow the model to understand the relationships between words, even if they don't appear in the same context. For example, the words king and queen might have similar embeddings because they are semantically related. These embeddings are generated by training the model on massive amounts of text data, allowing it to learn the statistical relationships between words. The embeddings are then used as input to the transformer network, providing the model with a rich and nuanced understanding of the input text. Furthermore, advancements like mixture of experts, MO, architectures are playing a significant role. Imagine instead of one large model, you have a collection of smaller, specialized models or experts. For any given input, the system dynamically selects the most relevant experts to process the information. This allows for greater efficiency and specialization, leading to improved performance on specific tasks. This helps with the code by increasing the ability of the model to handle diverse types of information. And let's not forget the importance of fine-tuning. After a large language model is pre-trained on a massive dataset, it can be fine-tuned on a smaller, more specific dataset to improve its performance on a particular task. For example, a model might be fine-tuned on a dataset of medical texts to improve its ability to answer medical questions. Or it might be fine-tuned on a dataset of code to improve its ability to generate and understand code. This fine-tuning process allows the model to adapt to specific domains and tasks, making it more versatile and useful. It's like taking a general-purpose tool and customizing it for a specific job. Beyond the architecture and training, the sheer scale of data is crucial. The larger the dataset, the more patterns and relationships the model can learn. This scale allows models like Gemini to achieve remarkable levels of accuracy and fluency. Think of it this way, the Gemini text code isn't just one single thing. It's a combination of sophisticated algorithms, massive datasets, and intricate training processes. It's the result of years of research and development, pushing the boundaries of what's possible with artificial intelligence. It's also important to remember that this technology is constantly evolving. Researchers are continually developing new techniques and architectures, pushing the limits of what large language models can do. We are witnessing advancements in areas like multimodal learning, where models learn to understand and generate text, images, and other types of data. This is expanding the code further, allowing for richer and more nuanced interactions. The ethical considerations are also a part of this evolving code. As these models become more powerful, it's crucial to address issues like bias, misinformation, and responsible use. The developers are working hard to ensure that these models are used for good and that they benefit society as a whole. So, when you see a large language model generating impressive text, remember that it's not just magic. It's the result of a complex and sophisticated system, a system built upon the Gemini text code. It's a testament to the power of artificial intelligence and the potential it holds for the future. It's a constantly changing landscape, and we're all witnessing the birth of a new era in how we interact with information. The Gemini text code is still being written, and we're all part of the process. With that said, thanks for watching, and until next time.